got about 10 more minutes, and I'm gonna join the Discord channel. All right, so
Zach, are you speaking on the Google Meet side?
oh, I forgot to put on the mic. There we go. So I should be speaking on both. Oh, Google Meet is muted, so let me.
We can. Oh, never mind.
I need to unmute. There we go. So now I should be on both, and also YouTube. Yeah, little things, just kind of threw off the routine because I got a new mic, and so that's a little bit different from usual. Not a whole lot. All right, so let's take a look. Okay, and I'm gonna put a link to the Discord channel and have it pinned. There we go. All right, so we got one person typing in Discord's text channel. So I'm gonna wait a little bit until I get that question. Okay, there you go. Got the question now. I don't know. My HyperX actually was still working fine. It's just that the noise rejection is not as much as I would like. With this mic, it is a whole lot better because I can place the mic much closer. Um, so it's just good. All right, so let's go ahead and get started with today's class, followed by there will be a lab later today. So in today's lab, you will need to know a few things. So we'll go ahead and take a look, take a kind of like a preview of what we'll be doing tonight. So we're starting to talk about branching, and how to translate C code, very simple C code into assembly code. And also how to perform arithmetic operations. So we'll be basically looking into conditional branches, unconditional branches, and also operations that are arithmetic. And one of these questions would also bring you all the way back to talk about 2's complement, because we'll need to take the arithmetic negation of a value in a register. So that would be tonight's focus. And let me get started with Logisim first, because that's definitely something that we need to use tonight, as well as the assembler and the opcode table. So all of those things we're gonna need for tonight. So we go to the shared folder and then go to processor. And here's the assembler. So we'll definitely need to open the assembler and also the opcode table, because I want to explain these few instructions for tonight. Oh, by the way, because I counted the number of people. Well, I didn't count, but YouTube did. So there were about less than 40 people opened the YouTube link that I recorded over the weekend. So that means about 20-ish people in the class did not open that link, did not watch the YouTube that I recorded after Thursday's class. So that means those 20 people either did not or do not know what to do over the weekend, or they have done that on their own without me having to tell them, how to prepare for today's lecture. Either way, I'm not going to change the way I'm going to lecture today. So conditional branches. So let's see what we should do. We should probably start with something that changes the flags. Okay, and to do that, we can take a look at the processor. and find out, in the architecture, how things are connected, how the components are connected um, inside the processor. So let me start Logisim first, and then we'll go from there. There we go. All right, so here's Logisim. Not a, you know, it's exactly the same as last time. So what we know as the flags, they are inside the flags register. So this guy over here, that is our flags register. So all the flags that we have talked about, the carry flag, the borrow flag, the sign flag, the overflow flag, and also the L flag, they are all basically contained in the flags register. But there's one more flag which is called the Z flag or the zero flag. That's also inside the flags register. So if you analyze, how we update the flags register, follow this link here. It appears in red. It's actually okay. It's not really a bad thing. It's actually okay. When we look into the ALU, we'll find out why that is the case. But it's coming out of the ALU. This is the ALU. So now we want to know, okay, but how do these flags, how are these flags computed? Because the ALU is responsible to come up with the value of the flags. The flags register is only here to remember, what the flags are, okay, so that we can use the flags for certain things. So now we right click on the ALU, and this is the inside the ALU. So inside the ALU, we track down the peripheral first. Okay, what are the inputs and what are the outputs? So we look into the input first. So the input, there's one input pin. Yeah, it does complain about that. We do not want to do that. So because I was using the poking tool, and I'm not supposed to be able to change these bits, when I'm just inspecting. So let me change back to the pointing tool here. So we do have, two input pins. This input pin goes to a demultiplexer, which means, one input and one of the output is going to connect to the input, and the same thing over here. So we have two input pins, and these are both 8-bit wide. So now we want to know, but which one are we selecting? In other words, this is the input. Which one of the output are we connecting to the input? That is determined by the gray dot. The gray dot is called the selection. So we track down the selection. Okay, and now I have to switch back to the poke tool, because the poke tool is really handy because it also highlights the entire node. So we can see the OPSEL, or operation selection, is a 3-bit thing because there are potentially 8 output out of these demultiplexers. So we need 3 bits to determine which one of the output is connected to the input of these demultiplexers. All right, so what are the output of the demultiplexers connected to? So now we track down the wires one by one. Output 0 and output 0, they're both connected to the adder. So this is how we perform addition operations. Output 1 and output 1, they're both connected to the subtractor. This is how we perform subtraction. Output 2, both of these are connected to the right shift operation. So the top one specifies the bit pattern that is to be shifted, and then the bottom one specifies how many bits we are shifting to the right hand side. Left shift we can do without a specialized circuitry because we can always add a register to itself. But when we are trying to right shift, there's no other way to do right shift except to do it this way. What about the next one? The next one looks a little bit curious because only one of the two inputs connect to that one. So when we track down this one, which is our output 0, 1, 2, 3, our output 3, it goes to this is a bitwise NOT. So it takes all 8 bits, and then for every single bit position, it is flipped. A 0 becomes a 1, and a 1 becomes a 0. What about the next one? We have output 4. It goes into an AND gate. This is bitwise AND. So every single bit position is ANDed with the other input, and then the result becomes the output. Now we have already used multi-bit gates in the past, especially when we talked about the carry look-ahead adder. So I'm hoping that you guys still remember, what exactly is a multi-bit adder. I mean, a multi-bit gate. In this case, an AND gate. And then the last operation is an OR gate, kind of the same deal. It takes one input from the top multiplexer, and it takes the other input from the bottom multiplexer. This particular multiplexer is kind of doing exactly the reverse of these two demultiplexers. This particular multiplexer takes the input from the output of the adder, the output of the subtractor, the output of the right shifter, the output of the bitwise NOT, the output of the bitwise AND, and the output of the bitwise OR. And its selection, it is also connected to OPSEL. So OPSEL, determines the switching of the two demultiplexers so that we can divert the input pins to the correct operation. And then the output is determined by the multiplexer. So it chooses from the right operation to become the actual output of the ALU. So that's kind of, generally speaking, how the ALU is structured and how it can perform all of these operations: addition, subtraction, right shift, bitwise NOT, bitwise AND, and also bitwise OR. Now let's take a look at the flags. This one is S out, which basically becomes the sign flag. Okay, this becomes the sign flag, and if you look at the splitter, it's a little bit hard to see it. Let me zoom in just a little bit. You can see how the splitter is taking the 8-bit coming out of the multiplexer, and is only taking bit 7 to become S out. In other words, S out is basically just the most significant bit of whatever the result is, and it's regardless of what operation we're dealing with. So that's the sign bit. The sign bit is always influenced by whatever operation we are performing. What about the other flags? Okay, excuse me, I got something getting into my eyes, so I need to take care of that first. So I need to take off the mic, so I can take off my glasses. All right, I'm back. Hopefully it's not gonna irritate my eyes any further, but we will see. Alright, so I think I need to move my mic a little bit closer like that. There we go. Alright, so do we have any questions about the sign flag? The sign flag is really just the most significant bit of the operation. So even though only the first two are going to deal with quote-unquote values of an integer, the other ones are mostly bitwise operations, they will change the sign flag regardless. What about the other flags? We're going to skip the Z flag, which is new to us, and we'll go ahead and focus on the flags that we are we know already. Okay, and two of those are fairly easy, the carry flag and also the borrow flag. These two coming out of the adder and also the subtractor, they are going into this multiplexer. And this particular multiplexer is it doesn't seem very smart, right? Because it has carry in going into 6 of the inputs of the multiplexer, and then only input 0 and input 1 are coming from the adder and also the subtractor. So what that means is if you're not performing addition or subtraction, it will just maintain the carry flag. All of the other operations, that includes right shift, bitwise AND, bitwise OR, bitwise NOT. Just one more. I cannot remember. Now I'm gonna have to take a look. I think those are all of the ones that are in use. So all of those other operations will just maintain whatever the carry flag was because it doesn't make sense, of asking, so what is the carry of this right shift operation? It doesn't make sense. Or what is the carry of this bitwise NOT? It doesn't make sense. So with all of those operations, the carry flag is simply, it would just maintain whatever it was, except for when we're doing addition, it would take C from the adder, and when we're performing a subtraction, it would take B from the subtractor, and that becomes C out. Now C out is going outside of the ALU, and it will be stored inside the flags register. So that accounts for borrow and also carry. So this is also kind of important because we have to remember that both the adder and the subtractor are using exactly the same bit. So that means, after a addition and you have a subtraction, the carry from the addition will now be overwritten by the borrow of the subtraction. And it's okay for the most part. I mean, it really does not cause any problems. Alright, so far we have explained carry, we have explained the sign. Let's take a look at overflow. So overflow is right here. So the overflow O out is determined by this little circuit here. So the top circuit is for adding, which is what your exam 1 has. This is how we determine whether, after an addition, we have an overflow when it comes to interpreting values as signed values. And then this one is the one that we are very familiar with, which is for subtraction. This is how we determine whether there's an overflow condition in a subtraction. So what it does is it will take S1, S2, and S out. We know that S out is really just bit 7, or the most significant bit of the result of an operation. What about S1 and S2? S1 and S2 are tunnels that are coming from the inputs right here. So just like how we extracted S out as bit 7 of the output, bit 7 of in 1 becomes S1, and then bit 7 of in2 becomes S2. So once again, we are using the minuend, the subtrahend, and the difference, the most significant bits of those 3 components, go through 2 AND operations, and they negate different inputs, and then we use an OR gate over here in order to determine the actual overflow bit. And then this multiplexer is here so that we can, after an addition, we'll use this particular node. After a subtraction, we'll use this particular node to connect to the overflow output, which then becomes one of the output pins, that we connect to the flags out connector, or output pin. So that explains O out. What about the L flag? So the L flag does not even have its own wire, because it doesn't need one, because it really is just the exclusive OR between the sign flag and the overflow flag. So this is basically the L flag. So you can see the L flag is bit 4, overflow is bit 3, sign flag is bit 2, carry out is bit 0. Then what about this Z out thing here? Because we haven't explained what is the Z flag. The Z flag is actually right here. So the Z flag is the NOR of all of the bits coming out of this multiplexer. In other words, when we look at the output of the ALU, the result of the computational operation, we take all of the bits, we take all 8 bits, okay, and then we perform one gigantic NOR, negated OR operation. The output of that becomes Z out. So if you think about it, okay, how can Z out become a 1? Z out becomes a 1 if and only if all of these bits are zeros. So when Z out is a 1, that means whatever operation we just performed ended up with a result of 0. And that's why it is called the Z flag for 0. Alright, so we got a question. I'm getting E and X blue and red wires instead of green wires. Okay, why is that going on? Very good question. So the reason why we got blue wires over here is because the enable of this multiplexer is a 0. So when the multiplexer is not enabled, the output is what we call floating. It's basically non-determined, and because it is non-determined, it is in blue. Now, if you feed wires that are non-determined into the input of a gate, and there's not enough information to determine the output of the gate, then the output of the gate becomes red because the gate still has to output something, but we don't know what it is supposed to output because we don't have a determined input for the gate at this point. Alright, so I'm looking at the text channel. There's a little bit of traffic there. The Z flag is useful because it is a very handy way to see whether the result is 0 or non-zero, because otherwise we'll have to check both ways to see whether it's less than, whether x is less than y or y is less than x to know whether they're different or not. Then the next question is, so if we subtract input 1 from input 2, it's actually the other way around. We subtract input 2 from input 1. We can use the Z flag to determine whether they're equal. Exactly, that is exactly right. The next question says you can check if two values are equal using Z flag. Exactly, so Marco is correct about that. After a subtraction or a compare, there's a slight difference between those two. Very good. And the last question is, why do the comparison ops use the Z flag, but increment and decrement do not? That is a very, very good observation. I'm glad someone actually notices that the increment and decrement operations do not affect the flags. The reason why that is the case is because increment and decrement, they are supposed to work with the registers, but I don't want these instructions to mess around with the flags register, because a lot of times, I would set the flags using a compare or similar operation, and then I need to perform something with a register. Typically, it would be the stack pointer, but we haven't explained what the stack pointer is at this point, so I can't really refer to that. But there are very good reasons why we don't want the increment and decrement operations to affect the flags register. Yeah. So that's pretty much the ALU. I mean, the ALU looks complicated. If you zoom out, there seems to be a lot of components, right? I mean, it looks like that, okay, like that. But if you think about it, it really is not that different. You can kind of look at it as there are like 5, 6 factories, right? So you have to divert, train tracks, because most factories require 2 components to make the product. So now you have to divert, the incoming tracks through these switches to one of the 6 factories. And then whatever factory is actually active, doing something, you want to take the output of the factory and merge that track with the output, because now you have 6 tracks merging at this particular switch, and you want those to be merged into one single output, so that you can say, oh, this industrial complex has one single track going outside, and to carry the product of whatever operation we want to specify. The flags register is kind of special on its own, okay, because it is here. So it's a separate output, compared to the actual result of the computation. So that's the flags register. Okay, so let's go ahead and perform an operation, okay, with one of these things. There are a few instructions that make use of the ALU. Let me point out what those instructions are first. Let's see. Most of them are down here. So this is bitwise AND, this is bitwise OR, this is compare, and there's also subtraction. I think subtraction is... They're not in this order. Okay, there we go. We have subtraction over here, and then we have addition over here, and then right shift is over here, and then bitwise NOT is over here. All right. So let's compare 2 instructions that are very close but not exactly the same. One is subtraction and the other one is compare. So this is subtraction and this one is compare. So you can see the two highlighted rows. One says x equals to x minus y, and the other one simply says x minus y. So the difference is whether we store the result or not. Compare does not store the result. It goes through the entire motion of doing the subtraction, but the actual difference is tossed away. We only want the flags to be affected, but we don't want the actual result to go back and update x, whatever register x is specifying. Subtract, on the other hand, will subtract y from x and then store the difference back into x. So that's the difference between these two. And compare is very useful because a lot of times we don't really want to change the minuend. We just want to see, who is smaller, or whether the minuend is smaller than the subtrahend or not. The z flag is only useful to see whether things are the same or not. It cannot determine whether the minuend is less than the subtrahend or not. That's why we cannot just use the z flag. The z flag is really a convenience feature. We could live without the z flag, but it would be kind of inconvenient when it comes to checking the result after a compare. So there's that. All right. So let's go ahead and hand assemble an instruction, put it into the RAM, and then we'll analyze it. Okay. So we'll do a compare. Okay, we'll do a compare, which is 1110 xxyy, and we'll just subtract. We'll subtract c from b. So xx would be b, and then yy would be c. So b is going to be a 0, 1, and c is going to be a 1, 0. So we end up with 1110 0, 1, 1, 0, which is a E6. So if you're not quite catching, how I figure out the bit pattern, you can listen to this part again. You'll just kind of make a note of the time right now, and you can go back to this point and listen to it again. Okay, because I did a lot of mental math in my head to figure out, what is XX, what is YY, and then I converted the 4 bits into a single hexadecimal. Then there are 2 hexadecimal in my head instead of using a table. So the end result is we have a E6. Okay. So now we switch to Logisim, go back to the main circuit, and zoom in again. There we go. And we'll go ahead and change the instruction here. Change this one to E6, and then change the next one to, I don't have to change the next one, but it's always a good idea just in case, we have quote unquote a runaway situation. We want to get into a halt instruction right away so that we don't end up, going through all the locations and then go back to the first one and so on. It's not 100% necessary because I'm just going to use Control T to single edge, this particular instruction. But it's really easy to do, and I go like, why not? Okay, so Aaron has a question coming, so I'm gonna wait for that a little bit. All right. So what we'll do is we're gonna single edge, but I'm not gonna talk about the fetch or the decode operation because we talked about that last Thursday already. And if you had watched the video that I sent you last week, you probably would have exercised and figure out, how the LD or the ST instruction work. So you probably already know. Okay, yes, I know the fetch instruction. The fetch cycle is going to do this, and then the program counter gets incremented, and then we decode, and then we get to the location that is specific to that particular opcode. Okay, so Aaron said, can I move the date below my camera? The YouTube bar covers it. The YouTube bar. Okay, let me take a look at OBS and see what it looks like. The YouTube bar. I don't see a YouTube
So,
bar.
like when I'm mousing through YouTube, the
Uh-huh.
time bar covers the time slot, so it's hard to see it. So you move
Oh,
the date like
okay.
your
Gotcha.
camera.
Okay, now I understand. And we can move that So you want it to be like here, maybe?
Yeah, that'd be very helpful. Thank you.
Sure. Easy peasy. All right. So now we can go ahead and get started with this. Before you start to single edge through the instruction, it's always a good idea to make sure that your clock is a 0. And if you don't know whether the processor is already in some state or not, it's always good to click this particular reset button, which does not clear RAM. Okay, this one is specifically only for the processor itself. It is not connected to RAM at all, and that's why RAM has its own reset button, so that I can reset the processor without resetting RAM. So I click this, and now we know we are starting from the initial state of the entire thing. Okay. So as I said a little bit earlier, I'm gonna fast track through the fetch, Control T, and then the program counter is incrementing, and then decode. So now this is where we're concerned, okay? Because this particular bit pattern coming out of location E60 is controlling the traffic, so that we have so that now we have configured all the components for comparing register B to register C, which ends up basically just subtracting C from B. Oh, that's just OBS. I did not realize OBS would actually record that. Actually, it depends on how we do this. Yeah. So let me lock it first. That is okay. Oh, I have lost track of my mouse again. Oh, there we go. Alright, so I think it's right click and then lock preview. There we go. So the red line should go away now. Okay, cool. Alright, so back to Logisim. So now we want to look at the pathways between the components. So once again, we want to go through every single thing to see what is active and what is not active. We look at RAM. Okay, RAM is quiet. It's not paying attention, so we can skip a whole bunch of questions when RAM is not in use. And then we check the usual suspects, right? The usual suspects would be the PC, the program counter, not getting updated, the instruction register, not getting updated. But the flags register is getting updated. Okay, so we see this green wire here, light green wire going into the enable of the flags register. Nothing in the register bank is going to be updated because EINEN, your input enable, is not a 1 for the register bank. And then we take a look at the ALU. The ALU has enable being a 1, which means we are going to perform some operation using the ALU. Okay, so now that we know the ALU is being used, we want to figure out where is it getting its input 1 and where is it getting its input 2. Okay, so that would be a natural question to ask. So we look at input 1. It's coming out of this particular demultiplexer. The first thing we want to confirm is this demultiplexer enabled? This one has an enable pin, but it is also light green, so this demultiplexer is in fact enabled. And then we want to know whether output 1 is the one chosen to connect to the input pin. So we click on the selection. The selection clearly says 0, 1, so everything is good. So that means whatever out 0 is connected in the register bank will get to input 1 of the ALU. Okay, so now we perform a similar analysis of in2 of the ALU. This one is a little bit more complex, not really by much, because it is coming from a multiplexer. The multiplexer select is FC. FC is a 0. So that means out of this multiplexer, input 0 is being connected to the output. So we track down input 0. And it's coming out of a demultiplexer. So this particular demultiplexer does not have an enable, which means it's always enabled. But now we want to know whether output 1 is connected to the input. So according to the selection, which is light green, it is a 1. So that means output 1 of this demultiplexer is in fact connected to out 1 coming from the register bank. Okay, so after all this analysis, the conclusion is out 0 is connected to in 1 of the ALU, out 1 is connected to in 2 of the ALU. So now the next question is, what is connected to out 0 in the register bank and what is connected to out 1 in the register bank? So we right click, we view reg bank. So now we look at this wire and then we track it down and go like, okay, it's coming out of a multiplexer. So how is this multiplexer selecting which input connects to the output? We see a register output 0 select being 0, 1. So that means input 1 is being used to connect to register output 0. And that's coming in from register B. So at this point, we know register B connects to in 1 of the ALU. Then we do a similar analysis of register output 1. And we ask, okay, of the 4 registers, which one connects to register output 1? The selection is specifying 1, 0, which means input 2 is connected to register output 1, and that's coming from register C. So at this point, we know register C is connected to in 2 of the ALU. All right, so let me check the text message. All right, so I'm hoping you guys, did spend some time over the weekend, to kind of track down the processor. But this is also why the lecture is recorded, so you can go through this again. So right now, it's kind of focusing on the main concept. How. So I mean, everything is recorded. You can always go back and watch the whole thing again. But right now, I'm showing you how to do something as well. So it's not so much which register is connected, it is how I analyze the circuit that is more important. Yep, and that's why you want to keep track of the timestamp. So that way you basically maintain a little list of time marks that you want to go back to after the lecture instead of watching the entire thing all over again. You can selectively just go to several spots and just kind of watch those portions again. Yeah, I understand that. Easier to absorb the discussion on the first pass. Yes. Yes. Okay, very good. Okay, I like Jackie's idea, which is to randomly inject some values. Let's not, well, do we want it to be random? Let's make it sort of random, okay? We'll make this one a 0, 1, and then we'll make this one an FF. I specifically chose these two values because 1 is less than FF is true when we look at things from the unsigned perspective, but 0, 1 is less than FF from the perspective of signed interpretation would be false. Okay, so I specifically chose these two values to kind of help you remember all those flag stuff when we talked about binary subtraction. All right, so I'm getting into the text channel and just reading a little bit. Exactly. So I think Rachel, I agree with Rachel. That's actually my intention, is to show you how I analyze the circuit. Not so much the detail. The detail, because I made the processor, so I kind of know my way around it. I'm really familiar with the processor. But it is how I ask the question. Okay, the ALU is active, so now we need to ask, what operation are we performing? How is it getting its input? How do we track it down? We use Logisim, we click on the node, we go back and then see, okay, it's coming out of a demultiplexer. So now we need to know how the demultiplexer is configured to make sure that, yes, that output of the demultiplexer is in fact active, driving the input of the ALU. There we go. I think you guys know about YouTube well enough to make your own playlist. So I'm not going to make it. Oh, somebody has already made it. It's a query, but it's close enough. Close enough. All right, so getting back to main. So now what do we do? Well, now that we know register B is coming out of out 0 into in 1, we know register C is coming out of out 1 into in 2 of the ALU. Let's go into the ALU and find out what it's doing. So this is something that we can do because at this point time has stopped. But even though time has stopped, we can do inspection. It's kind of like a debugger at a breakpoint, right? I mean, we can print, we can look at the variable, we can do some calculations, and we can even inject values back into the registers, right? So this is really handy, okay? And this is partially why I'm using this processor in Logisim to teach the architecture part of this class. So right click, view ALU, and now we say, okay, so this is 0, this is 1, and this is all F's. We know how in 1 and in 2 got these values, so that's good. And then the next thing is, so which operation is active here? So we check out OPSEL, or operation selection. It is 0, 0, 1, which means of all the demultiplexers, we pay attention to output 1. Of the inputs into this multiplexer, we pay attention to input 1, and same thing over here, same thing over here. So we only pay attention to channel 1 of all 8 channels. So channel 1 turns out to be the subtractor. So we click on this wire, make sure it is 0, 1. We click on this wire, make sure it's FF. If you're not seeing FF, you should probably be seeing -1. If you have not changed the settings of Logisim, when you do this, you probably will see -1 because signed base 10 interpretation as the second number after the slash is the default. I changed mine to hexadecimal, and I think in one of the previous classes I showed you guys how to do that also. So if you have done that, great. Okay, if you haven't done it, you might want to consider doing it because at this point I would say the hexadecimal representation comes in pretty handy. All right, so you probably would guess the next thing I'm going to click is this wire. Yes, but not yet, because I want to know what it is supposed to be before I click it. So what we have here is 1 minus -1. Or you can also look at it as 1 minus 255. Either way, the answer is 2. So we want to click on this wire, and it is indeed 2. So now this is the fun part. Okay, the fun part is it actually ends up with a borrow of 1. But it's not surprising, right? Because I only got $1 in my pocket. The bully out the door wants $255. So I'm going to go to the bank and borrow $256. Combining the $256 with the $1 in my pocket, now I have $257. And the bully takes $255, so I end up with $2 in my pocket, which is here. But at the same time, I have to remember that I owe the bank $256, and that's why the borrow flag is a 1. So this is looking at things, from the perspective of unsigned interpretation. What about the signed interpretation? Well, the signed interpretation is a little bit more involved because we have to look into this particular circuitry here, right? So this circuitry looks at the sign of the minuend, which is 0, 1 in this case. It looks at the sign of the subtrahend, which is FF in this case. And it also looks at the sign of the difference, which in this case is 0, 2. In order to determine do we have an overflow, the answer is no, we do not have an overflow situation. It is perfectly okay for a subtraction, for subtracting a negative quantity from a non-negative quantity, ending up with a difference that is non-negative. That's perfectly okay. So we do not have an overflow situation. But the L flag is the exclusive OR, between the sign flag and the overflow flag. The sign flag is a 0 because in the hexadecimal representation of 02, the most significant bit is a 0. That's why the sign flag is a 0. The overflow flag we just explained, the exclusive OR of 0 and 0 is a 0. So the L flag, if you remember from the discussion of binary subtraction, reflects whether the minuend is less than the subtrahend using the signed interpretation. And this is perfectly correct, right? Because 1 is not less than -1. We good. So, and then some of you are going to say, okay, we want overflow. I want to see a case where it does overflow. Let's do that. And without clocking the whole thing. Because right now, the multiplexers and demultiplexers, they are static at this point. So the routing part is static. We're not changing how things are routed. We are only changing the source of the things that are already connected. So now we can go back into the register bank and we say, let's make it overflow, okay? And to make this overflow, we just have to make this 7F, okay? Because 7F is the largest non-negative value in signed representation. So when we subtract -1 from the largest value that can be represented, it's going to wrap around to the smallest negative value. So that will cause an overflow. So now we go back to main, we go into the ALU again, and then we scroll all the way down, and sure enough, the overflow flag is now a 1. Okay, we can see it over here. And at the same time, because the sign flag is also a 1, 1 exclusive or with 1 is still a 0. What does that mean, Tech? Well, it means 7F, which is representing 127, is less than FF, which is representing -1, is false. So I'm hoping all of that stuff that we talked about when we talked about binary subtraction is coming back at least a little bit. All right. Z out would still be a 0 because the result is non-zero. Okay, so that means somebody is going to ask, so how do we make Z out a 0? Well, that's easy. That's easy peasy. All we have to do is to say the two values that we are comparing are the same. So now we have 7F and 7F. Now we go back to main, go back into the ALU, and now the Z flag is a 1 because the result is 0. Okay, we can see the result is 0, and as a result, the Z flag is a 1. All of the other flags are also 0 because there's no borrow in this case, and it shows as a carry by the time we get to here. But so basically, carry and borrow are the same thing when it's getting out of the ALU. The sign flag is a 0, and the overflow is also a 0 in this case. Oh, okay, I didn't know that. Thank you, Nathan. That's a pretty handy way to navigate around. So you're saying that I can just switch to register bank by clicking here. Cool. Oh, all right. Good find. Thank you. All right. Cool. All right, so now if I do a Control T in main, the value is going to be stored in the flags register. You can see the input of the flags register, which is this wire. This wire over here is no longer red because now we actually got circuitry connected to all the gates. So now the output makes sense. Okay, and that's why the wire is not red anymore. And it is 0, 2. And if you look at the bit operation, the Z flag is the only one that has a 1. The carry is a 0. The sign is a 0. The overflow is a 0. And then the L is also a 0. So if I do a Control T right now, it will simply remember this into the flags register. You can see how the flags register content is also 0, 2 at this point, right here. And when I do another Control T, it will go back to the fetch cycle again, and this time we'll get to the halt instruction, which is not very exciting. So this is how things get computed. Okay, the ALU, which is the arithmetic and logic unit, is the only thing inside the entire processor that knows how to add values, subtract, right shift, bitwise not, bitwise and, bitwise or, that sort of stuff. Okay. So the next question is, how do we make use of the flags, right? So now we go back to, I need to look at the time to make sure I got enough time to do this, and we do. So now we look into the the opcode table. So when we look at the opcode table, I know there are two sets of instructions that are very similar. Typically, we do not touch these. Okay, so JL, JO, JS. So these conditional branches without an I, they can be used, but they are rather clumsy to use. So we don't use those most of the time. And so we basically use these most of the time. But what I'll do first is to illustrate the Jmpi instruction. It is the unconditional branch instruction. So the unconditional branch instruction is simply the same thing as a goto in C or most other languages that your other professors have told you time and again, do not use, right? Well, guess what? In this class, you don't have a choice. You have to use goto, because assembly language programming has no structure, no inherent structure to the language itself. So to create a loop, you have to use branches. To make a conditional statement, you have to use branches. Never heard of it. What is it referring to, Aaron? Goto. Oh, okay. Well, that's because most of the time we call it the G word, because it's a word that we do not even want to pronounce. It only makes for good spaghetti when it is not used correctly. All right, so we're going to test the Jmpi instruction now, and you can also see what it is actually doing. It basically says the program counter gets whatever the program counter is pointing to by the time we get to that microcode specific to the Jmpi instruction. Tech, what does that mean? Well, that's exactly what I'm going to illustrate. Okay, so let's go ahead and illustrate it using a program. All right, so the program, I'm going to reset the processor. So once again, I need to make sure the clock is not a 1, and then we can reset the processor itself. And actually, in this case, I could have just reset the entire simulator because I intend to change the RAM content anyway. So the first location of RAM, I'm going to put in the opcode of 00. You guys go like, but Tech, you never talked about the opcode of 00. Well, you can look it up, right? I mean, you can look it up in the opcode table, and it is right here. It's basically just the no op operation. That's it, okay? And we're going to single edge through the no op operation, just so that you know why it is a no op operation. How can you make an instruction that doesn't do a single thing? It's actually pretty easy, okay? So we'll single edge through the no op instruction. Okay, so the next instruction we want to do is a Jmpi instruction. So we go back to the opcode table, we look up Jmpi. It is a 40. Okay, so now we switch back to Logisim and then punch in 40. And then it is asking me, where do I want to go back to? So this byte, the byte that is highlighted in red right now, is actually is representing the location where I want to continue execution. So right now it's telling me to go back to location 00. That doesn't seem a lot of fun. Let's make it go all the way to FF. That's more fun. Okay, so we'll go ahead and trace single edge through this program, mostly to find out what Jmpi is doing. Okay. All right. So as I said, I am going to single edge through this particular one. So we have the decode, right? So we have fetch first. So Control T. This is the fetch. So after the fetch operation, the instruction register has 00. Well, it's expected, right? Because we did fetch from location 0, 0, which has a content of 0, 0 that's put into instruction register 0, 0. Control T, we increment the program counter. Oh, I think I need another Control T to increment the program counter. So the program counter is now incremented by 1. And then the falling edge at this point is the decode. So now the question is, what is it going to do? So we're going to decode, and so okay, yes. So what do you think the decode cycle is going to do? The decode cycle takes whatever the instruction register has, and then left shift it by 4 bits, and then store that into the microcode pointer. Can someone tell me what is 0, 0 left shifted by 4 bits? What is it? What does it look like?
0, 0, 0, 0, 0, 0, 0.
Well, basically 12 zeros in binary or 3 zeros in hexadecimal. Very good. Okay. Then you guys will go like, but Tech, isn't that the first instruction of ROM and that's the fetch cycle? Yes, exactly. That's why the no op instruction has an opcode of 0, 0. It doesn't even need that 2 followed by all the zeros to get back to location 0, 0 because the instruction opcode itself is 0, 0 already. So when we decode this particular opcode, it naturally goes back to location 0, 0, 0. Okay? So when I type Control T, no surprises. It just goes back to 0, 0, 0. Alright, so now we are ready to execute the Jmpi instruction, because in RAM we can see that we are ready to get 4, 0 and do something with it. So this time I am going to fast track through the first 2 cycles of executing instructions, and will only be concerned about the execute cycle. Alright, so now we have the fetch, PC increment, and then now we have decode right there. And after the decode, we are now at location 400 in ROM. So now we want to see what is going on here. Alright. So if you have kind of played around with instructions, especially the LD and the ST instruction, you probably know your way around the processor a little bit by now. So we look at the RAM first, and we go like, okay, can we skip all the questions related to RAM? Unfortunately, not in this case, because RAM cell or RAM select is a 1. So that means, okay, now we have to track down a few things. First of all, are we reading or are we writing RAM? The answer is we are reading from RAM. So now next we need to know who is specifying this location. Okay, this always ends up with this multiplexer. So now we need to track down which input connects to the output. And according to the select pin, input 1 is connecting to the output, and then input 1 goes to the program counter. So now we know the program counter itself is driving the A port of RAM. It is specifying where we're supposed to read. Now the next question is, well, so somebody should be paying attention to the data port of RAM because we are reading from it. So now the question is, who is paying attention, right? So we track down a few things. This demultiplexer is turned off, okay, so that's good, because otherwise we can end up with a bus fight. We'll talk about that in just a little, maybe in a future class, but it's okay, because right now the demultiplexer is not selected, so we're good. The instruction register is not enabled, it's not going to update. And now we look at the input into the register bank. Well, input enable is a 0, so we know none of the registers inside the register bank is going to be updated. Another dead end. And let's click on this wire again. It goes into this multiplexer. So with this multiplexer, the select is a 1, which means input 1 is indeed connected to the output. So now we need to track down this multiplexer. And this multiplexer also has a select of 1, which means input 1 is connected to the output. And, oh, okay, it's going back to the program counter. And the program counter is enabled because you can see PCEN is a 1. So we are going to update the program counter using what the program counter is pointing to in RAM. That completes the whole analysis of what this cycle is going to do. And you can also poke on the wires too. If you poke on this wire, you can see it's already FF. So that means we are going to update the program counter to FF on the next rising edge. So there, Jonathan is typing Spider-Man pointing at Spider-Man meme. I think there's one indirection in this whole thing. Yes. So now, when we do a Control T, you can see how PC is now updated to FF. So FF is right here, and the question is, so we are at the end of memory, and according to Flat Earth people, the next instruction, or after we execute this no-op instruction, we're going to fall off the edge, and something bad is going to happen. Fortunately, even in programming, it is not flat. Everything is modulo, right? It's modulo 256 in this case. So it really just kind of goes back to location 0, 0. So if you don't believe that, it's okay. We'll just go ahead and just Control T a bunch of times. So now we have fetch, increment PC, decode, and you can see how we just got back to location 0, 0. So it's basically an infinite loop. Okay, this is a very weird looking infinite loop, but it is an infinite loop. All right, so that illustrates unconditional branch, which is Jmpi. I'm just looking at the time right now. It's 6:31, so we have about 21 minutes to talk about conditional branches. So conditional branches, let's look at the opcode table first. So in the opcode table, it is explained that a conditional branch is like this as a C assignment statement. So the first thing is using a ternary expression. The ternary expression uses L in this case to determine which expression we should be using to update the program counter. So if L is non-zero, then we're going to use whatever the program counter points to update the program counter. And then somebody's going to say, but that's the same thing as a Jmpi instruction. Yes, indeed, but only if the L flag is a 1. What if the L flag is a 0? Then we're going to update the program counter with the program counter plus 1. Then you go like, but isn't this going to skip an instruction? Whatever instruction is after the JLI instruction in this case is going to be skipped. No. What we're skipping over is the byte that specifies in case we do want to branch where we're going to branch to, we're skipping over that particular byte. Okay? So now we want to kind of play with at least one of these 5 conditional branch instructions, and I think we're going to play with JZI. Okay, so branch if and only if the Z flag is a 1. And also, by the way, in the English documentation or description, I use the word IFF. It is not a typo. I intentionally use IFF instead of just IF, because IF is if, IFF is if and only if. And in this context, it is appropriate to use if and only if and not just if. Okay, but this is not a logic class. I'm not going to get into that. The first part of the ternary operation or expression is a condition. You can look at a ternary operator as a if then else. So the first one is the condition, the second one is the then value, and then the last one is the else value. Alrighty. So I'm keeping an eye on the text channel, but otherwise, let's go ahead and test run the program. Alright, so make sure that the clock is low. reset, and I'm going to hand assemble a program again. So we'll keep our compare operation from last time. If I remember correctly, the opcode was E6. There we go. And now we want to specify a conditional branch instruction to go to a particular location. And so let's go ahead and look up the opcode table. I cannot remember the actual opcode, but once I look up, I know how to deal with it. So we want JZI, which is a 4-5. There we go. So 4-5 is the opcode, and now we want to say if it is indeed 0, where do we want to go to? Let's keep FF over here, and then we'll put a 0, 1 over here. So now we have a conditional branch. In other words, if registers B and C are indeed the same, we want to continue execution at location FF. If not, we want to continue with the 0, 1, which is a halt instruction. ALU flags are cleared only at the beginning. When you reset, when you hit the reset button over here, that is also connected to the flags register, like here. So that would also get cleared when you hit the reset button for the processor. There we go. Okay. All right. So let's go ahead and play with this instruction. It starts with a compare. Okay, so that is, so how do we want to do this? Do you guys want to do this where we are actually branching, or do you want to do it where we are not branching? Well, how about this? We'll just go ahead and set this up. I know there's a better way to do this, but this is like muscle memory. We'll make them the same. Okay, so we'll make it branch this time. Okay, 7F and 7F. And then we go back to main, and now we just single clock until we get to 4, 5 as an instruction. Okay, so we go Control T, Control T. Now we are comparing, and now we are fetching the 4. We have just fetched 4, 5 into the instruction register, and now we increment the program counter. So this is also kind of important because at this point the program counter is already pointing at the FF. Okay, whether we choose to use the FF or not is up to the microcode of the opcode. Okay, so the next Control T is going to it's a rising edge, and now we are. Oh, that was a falling edge. Sorry, I looked at the wrong wire. So it was a falling edge already. So now we have decoded the JZI instruction. So now we want to look at the configuration of the processor and find out how does it do this conditional thingy, right? Okay, so first thing first, we look at the flags register. It has 0, 2 in it. So does that mean the Z flag is going to be a 1? Well, the ordering of the flags is determined by two things. One is inside the ALU. If you scroll all the way down, this is how we configured the bits, and you can see how Z out is connected to bit 1. So the Z flag is indeed bit 1 of the flags register. So that's how we know, yes, the Z flag is a 1. So now the question is, how are we updating the program counter? You can see the program counter is enabled. It is about to be updated. So right now we can see the pathway. RAM is enabled, and when you look at this wire, there's a select of 1. So input 1 connects to the output, and then this wire is also, this multiplexer also has a 1 as the select, and as a result, this wire is also connected to the program counter, and that's why when the Z flag is a 1, the JZI instruction will use whatever the immediate operand is to update the program counter itself, much like the unconditional branch instruction. Then the question is, what if the Z flag is a 0? So now So you might want to time mark this, okay, because this is the fun part of understanding how the JZI instruction work. Okay. So remember, the pathways are static, but not the content of the registers. So I can inject a value into the flags register, like 0, 0. Okay. So when I inject a value of 0, 0 into the flags register, the Z flag is now a 0. Okay. So I'm just changing it on the fly so that now the Z flag is a 0. So now we want to analyze the whole thing again and see how we're updating the program counter. So we track down the input into the program counter. It is coming through this multiplexer, but you can see how PC mux this time is a 0 instead of a 1, which means we are using the incrementing mechanism. Just add 1 to whatever program counter has in order to update itself. So this is how the program counter is just incrementing in order to skip the location that contains the address of where we are supposed to go in case the Z flag is a 1. But in this case, the Z flag is not a 1, so we really just want to skip the location that contains FF onto the location of 0, 1 as my next instruction. So this auto increment will get the job done. So now the question is, how does PC mux know whether we are supposed to use FF to update the program counter, or whether we're only supposed to increment the program counter or not? So interestingly, the PC mux tunnel is not really directly connected to the ROM. PC mux is right here. In other words, PC mux is actually the output of this multiplexer. And what does this multiplexer do? It has a PC mux mux. It is called the PC mux mux because it is a mux. It is a specification to select the output of another multiplexer. So it's a multiplexer's multiplexer. That's why it's called PC mux mux. So this thing is specifying 0, 0, 1, which means input 0 is connected to the output. So whatever PC mux is getting, which is used here as well as here, is really determined by input 1 of this multiplexer. So where is input 1 connected to? So we track down this is bit 1 of a splitter. The splitter goes into the output of the flags register. And we have just talked about how bit 1 of the flags register is the Z flag. So this is why we can do a conditional branch, because we are just using the flags register, one of the bits of the flags register, to become PC mux, and then PC mux in return will choose one of the two inputs of this multiplexer to choose how we want to update the program counter. That is how the conditional branch instruction is, how it configures the processor to achieve the result of a conditional branch. All right. So if we keep it the way it is not going to jump to location FF, and instead the program counter will increment to location 03, and then we'll just halt. So we'll go ahead and finish this operation. So another control T will update the program counter, which is right here from 02 to 03. And that concludes the actual execute cycle of the JZI instruction. And then we get to the next location, which is 2 followed by all zeros, which goes back to the fetch operation. And this time we're going to fetch the halt opcode, which means at this point, after the decode, it's not going to go anywhere. So that is kind of what you need to know for tonight's lab. For tonight's lab, I will need a little bit of time to clarify one of the questions before I release it. So it's going to be it would just take a little bit more time for me to release it than usual, because every semester there's always a question and it's not clear in the question how I want it to be answered. So I want to be extra clear this time. All right, so we have 5 minutes before we take a short break before the lab starts. So let me see if there are any questions. Now would be a good time to ask questions. about the content that we have just talked about? Well, since there are no questions, oh, okay, there we go. We got some questions coming. It's not a big deal if the ALU flags do not get reset, but they do get reset. Because the reset operation is attached to this button here. So whenever I reset the processor, the flags register also gets reset. The problem with the flags register not getting reset is it will get the leftover flags from whenever. So if a program is properly constructed, it wouldn't be a problem because we wouldn't be looking at flags that are just random. On the other hand, with a program that is faulty, then it might look at a flag that is not determined by a compare instruction. It's just whatever is left over. So in that case, it can be an issue, because if you have a leftover of a 1 instead of the default of a 0, the program may do something different. Even though it's the fault of the program itself to rely on a flag that is not determined, but the symptom can change depending on whether the flag is reset by the reset button or not. So that's that. But I think it's kind of important for me to emphasize that there's no mystery with this processor at this point. Okay, every single opcode is already outlined in the opcode table, which means you guys can go ahead and experiment with all of these opcodes any way you want. Now, for those people who say, yeah, I tried this once and twice, I know how to assemble these opcodes, but I don't want to do this for every single program that I write. It's okay. Use the assembler. Okay, that's what the assembler is for. Okay. On the other hand, I kind of expect people to know how to figure out how these instructions work. Okay, so in other words, if I just point to a particular operation, like increment, okay, how we increment a particular register, okay, which is really just plus x, or decrement, which is minus x, okay. This one does not update the flag register, and if somebody is curious of how can it not update the register, how can it not update the flags register, I expect people to be able to assemble a particular opcode as an example, and single edge through the execution in Logisim to explain to that person himself or herself why the flags register is not getting updated, but the register is getting incremented. And also the next question is, where is the 1 coming from, right? Because in order to increment x, you're adding 1 to whatever the register had. Where is that 1 coming from? Where's that constant of 1 coming from? Once again, it is completely open sourced, which means the processor architecture in Logisim should be able to explain every single thing about the opcodes and instructions at this point. Okay, the more you get into this to try to figure out how things work, the more familiar you're going to get with the processor, which helps with the next exam, because the next exam is going to have one question, at least one question, that talks about the computer architecture. So the more familiar you are with the processor at this point, when you have time to kind of look around, poke around, experiment, then the less time you're going to have to spend in the exam itself just to find, oh, where's the program counter? Okay, you don't want to waste time in the exam just to find where a component is. I think we're in week 9 right now, so we have another 2 weeks or so before exam 2. Oh yeah, spring break. I personally do not like spring break because it just it's 1 week, that puts a damper on everything. So the next question is, can pretty much any sequence of opcode be loaded as long as halt is the final opcode? You don't even need halt as the final opcode. The program just won't stop automatically. Yes, we do get a break. I think at the school will mandate that I cannot teach when there's a spring break. All right. All right. So, it is 6:50 right now, so I'm gonna release the lab at about 7 o'clock, but I'm gonna go offline. I mean, if you guys want to watch, that's fine too. It's not a problem. So, but I do need to change the wording of one of the questions in order to make it more clear. And it's perfectly okay for you guys to watch this because it is one of those questions where the answer is open-ended. So it's not a multiple choice or fill in the blanks. Oh, the password, I'll get to it. So the passcode is JXI right here. So I'm gonna type it in the text channel, JXI, and I'll pin it. There we go. But you won't see it yet, because I need to change that one question first. So you guys can see how I changed that question. Okay, so we got this, this. Alright, so this is the one where I need to change the way I ask the question. Alright. Okay, I'm going to change this part here. In the following space, write down the number of iterations for each of the JXI instructions. Okay, that should do it. That should clarify everything. And I want to make sure this is an essay question. Yep, it is. Alright, update question. And go back to details so I can set the due date, which is 9:50. So today is March 16th. I'm just double checking the date. Yep, it is March 16th. And we're gonna set the time to 9:50 p.m. March 16th, 9:50 p.m. Save and publish. So now you guys should be able to access it. Yeah, you can eat food and program at the same time. I heard that it's not good for digestion because your stomach, your digestive tract is trying to compete for blood flow with your brain, and I think your guts always wins. Oh, essay question simply means it's open-ended, editing. So it will give you a text editor. You just have to type your answer. It's worse for your keyboard. Well, it depends on what your food is. If you have Ensure, it doesn't really touch the keyboard much. If you have deep fried chicken leg, that may be a little messy. Oh, that reminds me, I should probably cook my chicken leg too, because I got it marinated since 2 days ago, so it's ready to be cooked. Yeah, ribs can take too long. Alright, so I think the operation is already fully specified. I mean, the instruction is fully specified. But I do want to point out one thing, okay? Just in case people want a demonstration of that one. Okay, so I'm gonna do this one last part here. So let me change. I'm keeping the program. I'm changing the last location to a 0, 1. Oh, okay. Change this one to 0, 1. There we go. Okay. Alright, so there's one little thing I do want to demonstrate is how do you trace a program? Now, when I talk about tracing a program, the instruction is actually in the notes too in the lab, but I want to kind of do one quick demonstration because I think it's easier for you guys just to see me how to do it instead of reading the instructions of how to do it. So when you want to trace something, you go to Simulate, and then you go to Logging. So it's basically called logging in Logisim, but it does the same thing as tracing. And you can select, basically what you want to trace. Including the this is the A port, of the entire design. So when we look at this port over here, this is the A port. This is if you select it, it's going to log that. So you have to find what you need to log. There are a few things that are really particularly useful for logging. The program counter can be very helpful, and there are two PCs over here. One is referring to the output pin PC, and the other one is referring to the register PC. They are the same, okay? Because when you look at the design, you can see how the output, the Q output of the program counter is going straight into the output pin of PC. So they are the same. So the program counter can be useful. The value of registers can also be useful. So the flags register itself can be useful. You can even trace memory locations, but since this program is not going to change a memory location, it may not be needed. Okay, so let's just say that we want the program counter to be tracked. Okay, so what you do is you select it and then you add to the other side. If you don't do a single thing, it is in base 2, which is not easy to read, especially if you want to use the Assemble tab to tell you, oh, we want to know whether we got to this location or not. So you want to change the radix, the radix, and you want to change it to either base 10, I think that's column V, or you can change it to columns base 16, which is column W. I personally like column W a whole lot more, so I just use base 16. So let's just say this is all you want to track. Then you can go ahead and close the window, and then you just full speed run the program. So we go to Simulate, and then we just turn on ticking. And this program doesn't take long to execute. You got to one of the two halt instructions. So now we stop the ticking, because without doing anything else, the registers are the same. So we did do the conditional branch to location FF. So now the question is, how do we know that we got to location FF? So you go back to Simulate, you go back to Logging, and this time we go to Table. And you can see how the program counter changes over time. It starts up with 0, 0. Well, that's the default starting point. It got to location 0, 1, which is the second instruction. It got to location 0, 2, because that's how we read the byte that tells us where to go when the Z flag is a 1. And that's why the PC being 0, 2 is also logged. But we can also see how the program counter also got to location F. The program counter also is updated to FF. That's during the execute cycle of the JZI instruction. And after we fetch the 0, 1, the halt opcode at location FF, it auto increments to 0, 0. Even though we never read from location 0, 0 again after the first time, the program counter got auto incremented back to location 0, 0, even though it is stuck in the halt instruction at location FF. So that's how you can use the logging feature. So in addition to the PC or the program counter, I personally find it helpful to know what we are doing at the location. So OP fetch can also be useful. So if you add OP fetch, so now we're logging two things. So when you log two things at the same time, then whenever at least one of them changes, it will create a new entry in the log. Okay, so let's go ahead and do the log again. Now it's going to append it to this table here, and I think there's a way to reset it. I cannot remember how to do it. It is in the help. It's in the help. If you read this section here about logging, it tells you everything that you need to know about how to set up the logging and how to reset a table because you need to know how to reset it, because you need to reset and recount for that question that I just modified. So you need to know how to reset the table after you perform the operation for one of the conditional branch instructions. You have to reset it to prepare for the next one. Because if you don't reset it, I believe all it does is to append the new execution to the old one. So we can do this again. So make sure the clock is low, reset the processor without erasing the program, and then we go full speed ticking again, and then stop the ticking, and then we go to logging, and then we look at table again, and you can see how it just appends it, right? So that can be very confusing when it's just appended. So you want to know how to reset the table. Okay, since I'm here, I might as well just tell you how to do it. Well, okay, I'm gonna look it up and find out how to do it. All right, so it doesn't say how to reset it. Huh, okay. Okay, so remove it, Adam again. Okay. All right, cool. So somebody figure it out. So Nathan and Gabrielle both, and also Omar, they all found out how to do it. So you just remove and then add those items again. So you go to selection, you just have to remove the items and then add them back again. I'm guessing that's what they meant. Well, if that doesn't work, you can always exit out of Logisim and then restart Logisim. You just have to reload the program into RAM. So that's a very sure way to reset everything. So I would do it that way if I'm not sure. Okay, all right. So I'm going to shut up and stop the live stream so that you guys can get started with your lab. There we go.